Hello everyone, welcome back to thermodynamic subject. We are going to continue our discussion about the steady flow devices. In previous session, I have introduced different types of steady flow devices like turbine compressors, fans, and also nozzles and diffusers. Today we start with another type of these steady flow devices, which is throttling valves. What are throttling valves? Throttling valves are any kind of flow restricting devices, like what you can see here. Here you can see three different types of throttling valves, which uh, most common one is an adjustable valve, which we can change flow uh, or mass flow rate, and also we can change velocity and pressure of the flow by this restricting valve actually, or throttling valve. The other type of these throttling valves is a pros plug, which can reduce the velocity and change the pressure of the flow. And the other type of this throttling valve is a capillary tube, which can change the velocity and pressure. But what is the objective or purpose of using of these throttling valves? Generally, these throttling valves are being used to uh, decrease the pressure of the flow significantly. When we reduce the pressure significantly by these throttling valves, its temperature also will drop, and it will change, and it is useful especially in different uh, cooling devices like refrigerant or air conditioners. But as you can see here, we have a similarity between these devices and the turbine as well. What is the difference between these two? However, both of them cause a pressure drop in the flow, but here we don't have any work uh, in the device or in a steady flow device. Then this pressure drop will show as a generally as a temperature drop in the working fluid as well. So as I said, this pressure drop usually is accompanied with a large drop in temperature, which is a useful properties for devices like refrigeration system or air conditioning application. If you notice in these uh, devices, we don't have any, if we write that energy balance equation, as I said, let me just start from the basic uh, equation. If we write like this, E in minus E out equal to d delta E of system divided by dt. This term is zero. Why? Because we have steady flow here in these devices. And then E in will be equal to E out. What are the E in if we just select our control system or control volume actually here for these devices? Like what you can see here for a throttling valve, you can see here adjustable throttling valve. This is our control volume, a portion of the tube, for example, or in the valve. You can see here we don't have any work in the system as input or output. Don't have generally also delta PE is zero, delta KE or kinetic energy usually is zero. And also we don't have any heat transfer in the system. This is due to the this fact that the size of these devices is usually small, and also the velocity of the uh, flow in these devices is high. So we don't have enough time or surface area for significant heat transfer. So heat transfer also will be zero. Then the change in the energy of the system is only due to change in the enthalpy of the system. So what we have for E in is H, and also for E out is H, which we can show as H1 and H2, H1 as input, H2 as output. Then the change in the, if we write that energy balance, we have only this term. And as you know about enthalpy, generally enthalpy is equal to U plus PV. U is internal energy and PV, or pressure, times the volume, or volume of the fluid, is called flow energy. And we can say that internal energy plus flow energy, which is enthalpy, is constant in a throttling valve. So because this summation is constant, but for sure before and after uh, of uh, mm, of a throttling valve, this internal energy or flow energy will be different, because as I discussed earlier, the pressure will drop significantly. Then if pressure drop, it means to have a constant value for this summation to be equal to U1 plus P1 V1. If P here is reduced, if P2 is lower than P1, it means with the same amount of V, uh, then it means U2 is increased. And vice versa. So during a throttling valve process, enthalpy, which is flow energy, and internal energy of a fluid remains constant. This is this term. And then it means the internal energy and flow energy may be converted to each other. This is what I said here. If U is increased, then PV will reduce, and vice versa. And this is helpful for devices, as I said, like air refrigeration or air conditioning. We will see in an example how it works actually. And if the working fluid is ideal gas, it as it is discussed earlier, the temperature of an ideal gas does not change during a throttling throttling process, because as uh, is discussed in a previous chapter, for an ideal gas, enthalpy is only a function of temperature. Then, because H is constant, it means if H1 is equal to H2, it means T also will be constant or remain constant in a throttling valve for ideal gas. So, for example, and this is important characteristic as well, and it will be used to select appropriate uh, uh, fluid or substance for air conditioning or refrigeration system. Here we have an example to see how this concept which I introduced you, a throttling valve, is being used in a refrigerator to cool down or to reduce the temperature of a working fluid. One common type of the refrigerant is refrigerant 134, uh, which is a substance, which is a common substance to be used in a refrigerant or in a refrigerator. We have this gas enter to a capillary tube, which, as I introduced in previous slide, is a throttling valve. This capillary tube is in a refrigerated, and the state of this refrigerant when it is entered to this capillary tube is saturated liquid, and its pressure is zero point 0.8 megapascal. Then it is throttle. Throttle means it goes to the capillary tube, and its pressure is is dropped from zero point 0.8 megapascal to 0.12 megapascal. So pressure is reduced due to these throttling. Then we need to determine the quality of the refrigerant at the final state. It means at the final state, after throttling, we have a saturated mixture, and some of the that saturated liquid is evaporated. And also we need to determine the temperature drop during this process. In other words, we need to find X and we need to find T2. Okay, let's see what should be our assumption. One, heat transfer from the tube is negligible. So we imagine we don't have any heat transfer in the tube. Two, kinetic energy change of refrigerant is negligible. This is our two assumption here to use that energy balance equation uh, uh, with, in very simple for a structure. As I discussed earlier, this capillary tube is a simple flow restricting device, and it is usually being used to cause a large pressure drop in the working fluid or refrigerant here. First, let's see what, as I discussed earlier, for this kind of devices, H1 is equal to H2. So let's first find this H1. We have properties like we know how much is the pressure at state 1. Pressure is 0.8 megapascal, it is given. And also we know we have saturated liquid at state 1 or entrance of this capillary tube. So P1 0.8 megapascal, saturated liquid. We need to go to table A12. If we go to this table for this pressure, first of all, because we have saturated liquid, we know that the temperature also is saturation temperature. So saturation temperature for this pressure is 31.31 degrees Celsius. We know this from table A12, which is the thermodynamics properties for this refrigerant 134A. And the enthalpy also, because it is mentioned, we have saturated liquid, is enthalpy for saturated liquid or HF at this pressure, 0.8 megapascal. So the pressure, the H1 and T1 can be found in this table. We can refer to this table, table A12, and find these properties according to the pressure and its state which is mentioned. What about the enthalpy at the after this capillary tube? As I discussed earlier, enthalpy at before and after this throttling valve is identical, so H1 is equal to H2. Moreover, the pressure at the exit of this capillary tube is given, which is 0.12 megapascal. So again, if we go to the go to this table, we can find for this pressure, we need to find HF and Hg, which are the uh, enthalpy for saturated liquid, enthalpy for saturated vapor for this refrigerant. And also for this pressure, 0.12 megapascal, we can find saturation temperature, which is negative 22.32 degrees Celsius. All of this information also come from this table A12. I will show you this in table as well. Then this and also we know H2 is equal to H1. We have H1, it is 95.48. We find these values from table A12. Then we need to compare our enthalpy H2. If we compare H2 with these HF and Hg, we found that H2 is between HF and HG, higher than HF, lower than HG. Then we found that, as we discussed earlier in previous chapter, we have a saturated mixture. For a saturated mixture, we need to find quality of the mixture by this equation. We have the enthalpy here. So X2, or quality of saturated mixture at state 2, or the exit of the throttling valve, is equal to H2 minus HF divided by HFG. HF and HFG, HF we have here 22.487, we find in table A12 for this pressure. To find HFG, simply we can write HF minus HG. Then, or simply we can write HG actually minus HF. We have HG, we have HF. This is HG minus HF. Then, by solving this equation, we can find X2, or quality of the saturated mixture at state 2, or at the exit of the throttling valve, which is 0.34. Then we have the temperature as well. To find the change in the temperature, how much the part of question is finding this quality. We found that. The other part is to find delta T, or the change in the temperature in the capillary tube. The initial temperature and the final temperature, we have that the initial temperature is we found in the table 31.31 degrees Celsius. The final temperature, we found it negative 22.32. Then simply T2 minus T1 will give us the delta T. T2, T1, and the change in the temperature in this capillary tube is negative 3.63 degrees Celsius. So you can see here, in this capillary tube, pressure is dropped from 0.8 to 0.12 megapascal, and due to this drop in the pressure, temperature also is reduced by 53.63 degrees Celsius. And this is the reason why we use this capillary tube actually, to reduce the temperature. Then this reduction of temperature can be used to cool down the surrounding, to catch the thermal energy from the surrounding to the system. And also it should be noticed that 34% of the refrigerant is vaporized during this throttling process actually. And the energy for this vaporization is captured from the refrigerant itself, because here we don't have any heat transfer from surrounding. This is because we assume that we don't have any transfer, and also we don't have any work in the system. So the required energy for vaporization of this amount of the refrigerant is captured from the refrigerant itself. The other steady flow engineering device are mixing chambers. Mixing chamber generally are the, in engineering application, are the devices that combine two different fluids and or different types of fluid with different properties, or same fluid with different properties actually. A simple example of such devices are the T-elbow of the ordinary shower, which actually are mixing devices. They mix hot water and cold water, and the output of this mixing chamber actually is a cold water stream, which we can manage the actually mass flow rate of the hot and cold water to determine the desire, or to adjust the desired temperature for the output flow from the shower. So here what we have actually, we have generally two inputs, two with two different mass flow rate to produce an output or a mass flow rate of the flow, which its properties like temperature, pressure, and so on is a combination of the those properties from those different flows actually. Or like what we can have, you can see here, uh, insulated mixing chamber actually, which includes the two different inputs, one of them with mass flow rate of m.1 with temperature of 60 degrees Celsius, the other one with lower temperature, hot flow, cold flow, and we have the m.1 for hot flow mass flow rate, m.2 for cold flow mass flow rate, and finally they will mix in a pressure, common pressure for both of the flow, and the output temperature will be a result of the mixing of these two different flows actually. And the m.3 also is the mass flow rate of the output. Then let's see how we can write that energy balance equation. If we write energy balance equation for an adiabatic mixing chamber like what we have here, first of all, as you can see here, we can assume that because it is mentioned we have an adiabatic mixing chamber, then we don't have any heat transfer. We don't have any work involved in this process, this mixing process. So W dot is equal to 0, and change in the kinetic and potential energy for such devices also can be neglected and equal to 0. So the change in the energy in the system is only change in the internal energy and flow energy. Internal energy U and flow energy PV. But as you know, we have a combination of them, H equal to PV plus U. So what we have here, we can use H for this kind of devices. At the entrance and exit of this mixing chamber, only enthalpy will change actually. And uh, according to this energy balance equation, m dot h1, which is for the one flow number one, and m dot 2 h2 is the energy uh, in terms of mass for the flow number 2. It will be equal to m dot 3 h3, which h3 is the enthalpy of the flow at the exit of this mixing chamber, and m dot 3 is the mass flow rate of the exiting flow actually. In an example here, we will see how mass flow rate of these two different streams are effective on the uh, or the properties of these two different flows actually are effective on the temperature and the mass flow rate of the exit of the mixing chamber. What we have here is a well insulated mixing chamber. We have two different flows. Hot flow, temperature is 140 degrees Fahrenheit, and T2, and the other flow is cold flow. Its temperature is 50 degrees Fahrenheit, almost 3 times higher, the high temperature. And the mass flow rate of the hot flow is m.1. Mass flow rate of the cold flow is m.2. And the exit or after mixing temperature of the flow is 110 degree Fahrenheit. As you can see here, this temperature is between the high and cold temperature. And also its mass flow rate is m.3. This mixing also is occurred in this constant pressure, which is 20 psi. Then what we are going to find for this example is actually the ratio of the mass flow rate of the hot to cold water. In other words, m dot 1 divided by m dot 2. How much is it to reach this temperature? Okay, let's see what should be our assumption. First of all, we have a steady flow process. It means because we don't have any change with time in the system, then delta m of control volume or change in the mass for our control volume is zero, and also delta E of control volume or change in the energy of the control volume is zero with uh, in the control volume actually. Two, the kinetic and potential energy are negligible, as also mentioned in the question instruction. And assumption number three is heat loss from the system are negligible because we have a adiabatic mixing chamber actually, or insulated mixing chamber. And also, it is obvious we don't have any work interaction in this process. First, let select our control volume or our system. Actually, we select the mixing chamber as our system, like this dashed line. Then, if you notice here, our system is the control volume. Why? Because we have a mass crossing the boundary of the system. So we have a control volume. And it is a steady flow because we don't have any change in the flow with time. To calculate the energy balance, first let's start by writing mass balance actually. Here we have two different flows as input to our system and one flow as output of the system. So this is actually the mass balance equation, m dot in minus m dot out equal to dm of system by dt. This dm system by dt is zero. Why? Because we have a steady flow. And m dot in will be equal to m dot out according to this equation, which m dot in to our control volume are m dot 1 plus m dot 2 this, and the m dot out of our control volume is m dot 3, which is at the exit of this mixing chamber. So m dot 1 plus m dot 2 will be equal to m dot 3. This is our first equation. Then we need to write energy balance as well. E dot in minus E dot out equal to dE of system divided by dt. You have already familiar with this equation. This term is zero as it is mentioned here. Rate of change in internal energy, kinetic, and other type of energy for our control volume is zero because we have a steady flow. Then E dot in will be equal to E dot out. What are the E dot in or rate of energy to the system? The energy comes to the system due to the mass flow rate to the system. Then we have m dot 1 h1 plus m dot 2 h2, which is the energy of the flow which comes to the system by hot flow. This is m dot 2 h2 is the energy of the mass of the flow, with cold flow which comes to the system. M dot 1 h1, m dot 2 h2, and the energy which go out, the rate of energy actually which goes out of the system is enthalpy. If we write this uh, like this, we have another equation actually which shows what are the energies to the system, what are the energy which go out of the system. We have only energy which come from the flow to the system. In other words, we don't have any q dot, we don't have any w dot, we don't have any kinetic and potential energy in our system, and we have only the energy which come to the system and energy which go to the system by flow, and energy which a flow has or contain the energy which we have for a flow is energy flow energy actually, and internal energy which is equal to h for that substance actually. So this is our second equation. First equation, second equation. Then If we combine these two equations, we know m dot 1 plus m dot 2 is m dot 3. Then the left side, we just keep it as it is. And instead of m dot 3 in equation number 2, we write this m dot 1 plus m dot 2. So instead of m3, we write this m dot 1 plus m dot 2. This comes from this equation m dot 1 h1 plus m dot 2 h2 equal to m dot 1 plus m dot 2 times h3. If we divide this equation to m dot 2, we can reach this equation, which in this equation y is m dot 1 divided by m dot 2. Let me just do this for you. M dot 1, so both sides of this equation we divide to the m dot 2. So we have m dot 1 divided by m dot 2 h1 plus m dot 2 divided by m dot 2 will be 1. So we just cancel them. h2 equal to m dot 2 plus m dot 1 plus m dot 2 times h3. We can write like this: m dot 1 divided by m dot 2 times h3 plus m dot 2 divided by m dot 2. We just cancel them. It will be 1 plus h3. So, and if we just write m dot 1 divided by m dot 2 as y, we will have this equation: y h1 plus h2 equal to, if we just bring out h3 from these two, h3 m dot 1 divided by m dot 2 y plus, we just bring out this h3, will be 1. This is our equation which we have here. So here we have this equation. We have y is the answer to this for this question. What we are looking for is this ratio: hot mass flow rate of hot flow to the mass flow rate of the cold flow, which is y. So we are interested to find y. First of all, let's write this equation according to the y. Then if we keep this like this, y, let me write here, y h1 plus h2 h3 y. We can write like this: plus h2 equal to y h3 plus h3. Then we just restructure it: y h1 minus y h3 equal to h3 minus h2. Then if we bring here, we just bring out y from this: y h1 minus h3 equal to h3 minus h2. Then y will be h3 minus h2 divided by h1 minus h3. So to find y, we need to find h3, h2, h1 to solve this equation. And if we find h for each one of these states, we will find the answer for y, which is the mass flow rate ratio actually. What are the h? H3, H2, and H1 are the enthalpies in these three different states. We have H3 here, H1 here, and H2 here. And as if you notice here, we have saturated liquid. It is mentioned also. Hot water. It is mentioned. We have hot water, cold water. We have saturated liquid actually in all of these three states. The saturation temperature of water at this pressure 20 psi is 227.92 degree Fahrenheit, and temperature for the water in our example is 140, 50 degree Fahrenheit, and 110 Fahrenheit. And all of these temperature are less than saturated temperature. Then what we have here actually is a saturated liquid, uh, and the temperature and the enthalpy which we need to find for H1, H2, H3 is enthalpy of saturated uh, at that temperature for saturated water. For example, H1, we need to find HF for temperature of 140 degree Fahrenheit. H2, we need to find HF as saturated uh, liquid temperature for the water at 50 degree Fahrenheit. We can find all of these from the table. We need to go to the table which shows the saturated properties for different temperatures, which is table A4E actually. The temperature which we have are 50, 110, and 140. Temperature we have here 50, 110, and 150. Then to find H, as I said, we need to find for saturated liquid. So for this is 18 for 50 degree Fahrenheit is 18 as it is mentioned here. As well for 110 degree Fahrenheit enthalpy for saturated liquid is 78, and for 140 degree Fahrenheit this enthalpy of saturated liquid or HF is 107.99. So we can find all of these enthalpies in that table, table A4E. Then substitute in this equation, which is equation which we found here, H3 minus H2 divided by H1 minus H3. We have H3, H2, H1, and if we just substitute in this equation, we can find Y, which is the mass flow rate ratio of the hot flow to the cold, which is 2. By this, we find the answer for this question. The other steady flow devices are heat exchangers. You may already know about this type of devices, which are very useful devices in industry, especially when we are interested to change temperature of a flow or a fluid without mixing with another fluid. So the structure of heat exchanger is more or less similar to the mixing chamber, which I had introduced in previous slides. The difference between this and that mixing chambers, is the here we don't have any mixing for the fluid. So these devices can be simple, like what you can see in this figure, to different concentric pipes, like what you can see here, to different uh, pipes with two different fluids. But as you can see here, the we have two different flows, maybe for different fluids or same fluid but with same substances with different temperatures. And as you can see here, we don't have any mixture between the flows. So the only changes here is the generally is heat transfer between these two different flows. From the higher temperature we transfer to the lower temperature flows. Then the uh, one of the flows inlet temperature will be high and its temperature will reduce, and the other flow which is being used to cooling, generally its initial temperature or inlet temperature is low and the final temperature will increase. This type of equipment or devices can be used to cool down something or to heat to cool down a fluid or flow or to increase temperature of that flow. uh, and according to the uh, control volume for this type of the devices, as you notice here, again we have uh, a control volume or open system. If we select the whole heat exchanger, like what we have here as our control volume, then uh, we have a mass crossing the boundary. For example, the mass fluid B is crossing the boundary of our system. Then we have a control volume and with single string. But if we select our control volume like what you can see here, then uh, fluid A is crossing the boundary of the system. Again, we have uh, a control volume. But the difference between these two different methods for selection of the control volume is to consider the heat transfer. If we select whole heat exchanger as our control volume, for that heat exchanger, the heat transfer of the control volume is zero. And if we select one flow as our control volume, then heat transfer is not zero. In an example, we will see how we can use these two different methods to select control volume, to find the temperature of the fluid and or other properties of the fluid at the entrance and or input and output of each one of these fluid. And as you can see here, we have two inputs, one for fluid B, one for fluid A, and two output for one for fluid A, one for fluid B. So we generally have two input and two output for heat exchanger. This is the most common type of the heat exchangers. And this is helpful, this type of heat exchanger, when we are not interested to mix different uh, fluids or substances. For example, we have water and refrigerant, then we are not going to mix them because their properties are completely different and also maybe effective on the whole process. Then to find the different properties for this kind of devices, we can write in mass and energy balance. If you write mass balance here, m dot 1, m dot 2, for example, imagine we have a heat exchanger like this. We have water as one substance, one fluid, which is flows from its input here, its output is here, and we have also one refrigerant. The other flow is for a refrigerant, and its input and its output here. This heat exchanger as can be used to reduce the temperature of the refrigerant. As you remember in previous examples, heat exchanger, the refrigerant like this 134A, after being used for cooling down of something by that throttling valve we have seen in previous examples, then its temperature is increased. To reduce its temperature, we can use this heat exchanger. Here, temperature of water is 15 degrees Celsius, cold water. Temperature of the refrigerant is 70 degrees Celsius, hot refrigerant. Then we use this cold water to cool down this refrigerant. Then we have it transfer in this pipe between the wall of this pipe and water. The heat is transferred from this pipe to the water, from the refrigerant through this pipe to the water. Only heat can transfer. And if we select our control volume, like what you can see here, then if we want to write the mass and energy balance for this control volume, then m dot 1 is equal to m dot 2, m dot 1, m dot 2, which are the mass flow rate of the water in the input and output of the or input and output of the water to the heat exchanger is equal to mass flow rate of the water, and m dot 3, m dot 4, because we have a single stream, single input, single output, is equal to the m dot r, or mass flow rate of the refrigerant. And here if we write that energy balance equation, again, it is a steady flow uh, device, no change in the energy of the system with time. Then E dot in is equal to E dot out. E dot in to our control volume. If you notice here, we have this energy, the energy come to the control volume by these two different flows, or the flow of these two different substances. Or in other words, m dot 1 H1 plus m dot 3 H3. This is m dot 3 H3, m dot 1 H dot 1. And the output of our control volume, the energy which go out of the control volume, is dashed line, is m dot 2 H2 and m dot 4 H4. So this is energy balance equation for this control volume. Then after we write the energy balance equation for this heat exchanger by selecting the control volume like this, or whole heat exchanger, we have this m dot 1 H1 plus m dot 3 H3, m dot 2 H2 plus m dot 4 H4. M dot 1 is, as I discussed earlier, is m dot W, so m dot W H1 plus m dot 3 is m dot R, so m dot R H3 equal to m dot 2, again m dot W, m dot W H2 plus m dot 4, which is m dot R H4. If we just restructure this equation, we will have m dot W, then bring this here, H1 minus H2 equal to, and then m dot R here. If we bring this to the other side, H4 minus H3. Then we can solve this equation to find the ratio of the mass flow rate for the water and refrigerant. If we have the information, we can find H1, H2, H4, and H3 for each one of these states which are mentioned according to the information which we have about the properties and substance for each one of these states. For example, here we have refrigerant with 70 degrees Celsius and 1 megapascal pressure. So we can find enthalpy for H3 from the table. In an example, we will see how we can use this equation to find the enthalpy, the mass flow rate, and so on for a heat exchanger. Here we have an example which is similar to what I have shown to you in previous slide, which is cooling of refrigerant by water. Here we have a refrigerant. We are going to cool it down by water in a condenser. Condenser actually is a type of heat exchanger. Then the refrigerant enters the condenser with the mass flow rate of 6 kilograms per minute. So we know how much is the mass flow rate of the refrigerant, or m dot R is equal to 6 kilograms per minute. And we know how much is its temperature and pressure. Pressure is 1 megapascal, its temperature is 70 degrees Celsius. And it leaves this condenser with temperature of 35 degrees Celsius. And it did not mention any other information about that. So we have this information about refrigerant. What about the water? Water comes to this condenser with 50 degrees Celsius temperature, and its pressure is 300 kilopascal. And it leaves this condenser with temperature of 25 degrees Celsius. So temperature of the water is increased, temperature of the refrigerant is decreased. What we are going to determine is the mass flow rate of the cooling water required, or m dot W, how much is it? And the heat transfer rate from the refrigerant to water, or Q dot from the refrigerant to the water. This is unknown for our in this question, which we are going to find. And also, we can neglect the pressure drop in this condenser. By this information, let's see how we can find the m dot W and Q dot R, or mass flow rate of the water and heat transfer rate from refrigerant to the water. Okay, first of all, let's see what should be our assumption to solve this problem. We need to assume that we have a steady flow process. We can use this assumption because we don't have any information about the changes in the uh, uh, energy or the mass flow rate uh, of these two different streams with time. So delta MCV, or the mass of the control volume, will be the change in the mass of control volume will be 0, and also the change in the total energy of the control volume also will be 0. This is first assumption. And also we can assume that kinetic and potential energy are negligible, and heat losses from the system also are negligible. Then Q dot is equal to 0. This is important thing here, because this Q dot is the heat transfer for whole condenser. So here the condenser is insulated, and for whole condenser we don't have any heat loss. And also it is obvious, the assumption number 4, there is no work interaction in this process. First, to find the answer for part A, or to find the mass flow rate of the cooling water, we select the entire heat exchanger as our control volume, or our system. And if you notice here, like what we have in these few examples, uh, we have a control volume here because the mass is crossing the boundary. So our system, which we have selected like the whole condenser, the dashed line, is a control volume or open system. And uh, we can select this control volume in different methods, but here we just select this like this, and this is according to what we are going to find. Actually later we will see why we have selected this control volume like this. And if we select control volume like this, we have two stream a steady flow process here, to flow, and they are steady actually. To find the answer for part A, we start by writing mass balance. It means, as we discussed earlier, delta E, delta M for control volume is 0, then M dot in is equal to M dot out for our control volume. M dot in for each stream, actually, we can write this equation. Then M dot 1, which is for water, is equal to M dot 2, equal to M dot of water, mass flow rate of water stream. And M dot 3 is equal to M dot 4, which is mass equal to mass flow rate of the refrigerant. Then by writing the energy balance equation, E dot in minus E dot out equal to dE system by dt, as usual for a steady flow a stream, this is 0, then E dot in will be equal to E dot out. Okay, what are the E dot in for our control value? For our control volume, we have this stream and this stream to the system. We don't have any work to the control volume or from the control volume or heat transfer from control volume, which we have selected here. We don't have any kinetic and potential energy. The only changes is due to these flows, different flows which come to the control volume. Then this flow, energy of these flows is PV plus U or H, which we can write like this: m.1 H1, this stream, plus m.3 H3, this stream, these two stream, equal to E dot out m.2 H2 plus m.4 H4. These two stream as the output of our control volume. As I said, this is due to the all of these energies are zero, and we have only energy which come to the system by that flows. So those flows will go out from the system because of those two different flows. Combining the mass energy and energy balance, like what I have done in previous slides, we can reach this equation: m dot w h1 minus h2 equal to m dot r h4 minus h3. Okay, now to find m dot w and m dot r, we need we need to find h1, h2, and h3 and h4 for our streams here. First of all, let's start with the water properties or enthalpies of water at the input and output of the condenser. Water in state 1, 15 degrees Celsius and 300 kilopascal. If we go to table A4, let me find that table A4, which we have here as well. For this temperature, 15 degrees Celsius, the saturation pressure is only 1.7 kilopascal. Then what we have here actually is compressed liquid. And as we discussed earlier, for a compressed liquid, we can approximately choose enthalpy for saturated liquid as enthalpy for this compressed liquid. So H1, which is enthalpy for this state, is equal to enthalpy for saturated liquid at that temperature, 15 degrees Celsius, which from table A4, which we can find this. If we find HF is 62.982 kilojoule per kilogram. What about H2 or state 2? Temperature is 25 degrees Celsius. And again here, because it is mentioned that we can ignore or neglect the pressure drop in the system. If you just notice here, we can neglect the pressure drop in the condenser. Then the pressure also here we can imagine is 300 kilopascal. So again here, because the saturation pressure is this much and the pressure which we have here is much higher than that, we have a compressed liquid. Again, we can select the enthalpy for saturated liquid at that temperature, which is 25 degrees Celsius, as the enthalpy for this compressed liquid which we have here. So HF, or enthalpy of saturated liquid at 25 degrees Celsius for water from table A4. Temperature 25, enthalpy for saturated liquid is 104. We can write here. So we found H1 and H2 for which are enthalpies of the water at the input and output of the condenser. What about H3 and H4, which are the enthalpies for refrigerant? Again, the information which we have here are the temperature and pressure. First, for state 3. For state 3, again, we need to go to the table for saturated mixture, which is this table. For this temperature, we need to find the saturated pressure. Here, actually, or we can, for this is a long table actually. I just put a half of this table because we need just that to find the values. But to understand in which state is this refrigerate and what is the state of the what is the phase of the refrigerant with these properties, we need to go this table 8 or a 11 actually. Then in table 11, if we just see here, this is one almost 1 megapascal. You can see here the saturated temperature and so on is 40 uh, degree. Then according to this, because our temperature here is higher than saturated temperature actually, then we can understand that what we have here is superheated uh, vapor of this refrigerant. Then to find the properties for this refrigerant, we need to go to the table which shows the properties of the superheated refrigerant, which is table 813. The pressure which we have here is 1 megapascal and temperature is 70 degrees Celsius. Pressure 1 megapascal, temperature 70 degrees Celsius. Then we need to find enthalpy for that, which is 303 degree Celsius, which we found it. 303.87 kilojoule per kilogram is enthalpy for state 3. For state 4, we need again to go to table A11. In this table, what we know is its temperature first for 35, which we don't have directly in the table, but is between these two. And if we go to this table and find and also about the pressure, again, we don't know how much is the pressure here, but it is mentioned that we can neglect the pressure drop. So again, pressure here is also 1 megapascal as similar or equal to the entrance pressure. So temperature 35 degrees Celsius, pressure 1 megapascal. If we go to the table, we can find temperature. This is saturated refrigerant, uh, which is our substance here. And for the temperature which we have is between these two. And if you notice here, the saturation pressure for a refrigerant with temperature of 36 degrees Celsius is almost 912 kilopascal, less than 1 megapascal. And for temperature of 34 degrees Celsius, this is 863.11 kilopascal. And because our temperature is between these two, then the saturation pressure for this temperature also will be between these two. But the pressure which we have here is 1 megapascal. It means what we have here actually is compressed liquid. In other words, the pressure here is almost close to the, because the uh, pressure which we have here almost close to these values. So we can assume that here which we have a saturated liquid, we have a saturated mixture actually, but because here the pressure which we have is close to the saturated pressure which we have here, then we can approximately use a saturated enthalpy for refrigerant with this temperature and this pressure. Then we can just use HF for this temperature as the enthalpy at the state 4. To find this HF, we need to go to the table and do this interpolation. Again, not between these two. For enthalpy, actually, we need to do that. Then for this enthalpy, so we have temperature, we have enthalpy 34, 35, 36 temperatures. Enthalpies are 248, or this one actually, uh, this one 99, 99. 0.41. We don't know how much is enthalpy for this temperature, and 102.34. So after we do this interpolation, we can find the enthalpy for that, which is 100, the number between these two enthalpies. So we can find this enthalpy by interpolation from table A11, which is the enthalpy at state 4. Now we have all of those enthalpies, H1, H2, H3, and H4, and we can find the uh, m dot w. We have H1, we found from table H2, H4, and H3, and also the mass flow rate of the refrigerant was given, which is 6 kilogram per minute. So by substitution, all of these properties or variables in the equation which we have here, we can find m dot w, or mass flow rate of the water, or required mass flow rate of the water to have these temperatures in the condenser, which is 29.1 kilogram per minute. For the other part of the question, which is to determine the heat transfer from the refrigerant to the water, actually, we need to select the control volume. We need to change actually the control volume. What we have selected for part A of the question was entire condenser. Here for part B, we just select the whole volume of the water as our control volume. So this is the control volume for previous example. Again, we select this, but we exclude this part, the tube which contain the refrigerant. Then if we select that, then we will have, for that control volume, we have the what we have for that control volume actually is this flow m dot h1, or m dot water h1, m dot water h2 as input and output, like what you can see here. If we write energy balance for our control volume, here control volume is volume occupied by water. Then for this control volume, we have this m.wh1, m.wh2. This is E dot in. This is a part of E dot out is m.wh2, just that. And as for E dot in, we have this m dot water, and also we have a heat transfer from this tube, because we have just selected the water. Then we don't have any mass coming to the water, uh, and we don't have any mass of refrigerant to the water because it is separated. Actually, we have a boundary around this pipe. It is not included in the control volume here. Then we have it transfer from this tube, actually, from the refrigerant to the water. So Q dot W in. We have a Q dot W in for the our control volume actually. Then if we rearrange this equation, we will have Q dot W in equal to M dot W H2 minus H1. M dot W we have calculated in previous part, 29.1 kilogram per minute. And H2 and H1 we have found in previous step. So finally, Q dot W in, or the mass or the rate of transfer to the water, or even as you notice here, if you notice here, Q dot W in is equal to Q dot R, or refrigerant. In other words, because we don't have any heat loss from this condenser, all of the temperature, which all of the thermal energy or heat, which is transferred from uh, water, is transferred to the refrigerant, and vice versa. Then this much of energy is transferred to the water, and this much energy is captured from the refrigerant actually. So Q dot W in is actually equal to Q dot R out or in. It depends on the control volume we select. So you can see here how the selection of the control volume is effective on uh, uh, calculation of different properties and to find the answer for different questions. Here, what we have done for part B is only selection of the control volume. This is important. This is our new control volume actually. The last device which I'm going to introduce you as a steady flow device are pipe and duct. These devices actually are mainly being used in industry to transport different gas or liquid. And during this transportation of the gas and liquid, generally and usually the mass flow rate or the flow is a steady flow. So we can consider this type of the devices, pipes and ducts, as steady flow devices. In these devices, we have also different type of the energy transfer, and it also depended on the selection of the control volume. And as you notice here, again, we have a control volume. Imagine we have a pipe like this, then and a hot fluid is flowing through that. If we select our control volume like this, we have a steady flow, and it is a control volume. It is open system. Why? Because we have mass uh, transfer or mass crossing the boundary of our system. So we have a control volume, and generally the usually maybe the heat transfer from the fluid to the surrounding from the pipe be significant. This is one reason why we use this assumption to have a steady flow process to find this Q dot out actually, which is transfer from the fluid to the uh, from the fluid which is flowing in the pipe to surrounding. Or we may have some different type of the work or energy to the control volume in the pipe or duct, like electrical work or shaft work actually uh, to the duct or pipe. We will see in an example how we can deal with these examples here for with these structures as well. And one common type of the these uh, devices which we intentionally actually use work input or energy input to change the energy of the flow in the duct or pipe is what you can see here, which air with this mass transfer come to the duct, then its temperature is changed. Why? Because we use wire, for example, like what you can see here, to increase the temperature of the air flowing through this duct to heat the room or house. This is a general application of the ducts to or and a hot wire to increase the temperature uh, uh, of the house or a room. If you write the energy balance for a structure like what you can see here, as I said, we have a steady flow, then E dot in is equal to E dot out, like other steady flow devices, which I have already introduced to you. But if we select control volume like this, then E dot in will be W dot E in, which is the electrical power. Electric power comes from this hot wire to the our control volume, and also we have the enthalpy or energy which come from the uh, fluid flowing to uh, our control volume m dot h1, and e dot out is equal to the heat transfer from the working fluid or from control volume to surrounding, or q dot out, and m dot plus m dot h2, which is the energy which go out from the control volume due to the mass transfer or flow which go out of the control volume. So w dot e in plus m dot h1 is equal to the energy rate of energy transfer to the control volume. E dot out is rate of energy transfer go out from the control volume, which are equal to this. And if we rearrange this, we can write w dot in minus e dot, we bring the left side is q dot out minus q dot out equal to m dot h1. If we write this part, if we rearrange this, we will have m dot h2 minus m dot h1, which will be, we just bring out this h1. If you remember, because generally what we have this structure, this duct is being used for air. If we have ideal gas or air, this m dot h2 minus h1 can be is equal to this m dot. We have seen this equation in previous uh, slide, m dot cp T2 minus T1, which Cp is the specific heat for uh, the ideal gas which we have, uh, which is the fluid flowing through the duct. In an example, we will see how we can use these equations to find the temperature or this T2 or temperature of the fluid at the exit of the duct and or the other properties. This example is actually illustration of what I told you in previous slide. We have an electric heater for of air in a house. We are going to heat or increase temperature of the house, air of the house by a electric heater. The structure of the heater is similar to what I have shown to you in previous slide. We have the wire W dot E in is, which is equal to 15 kilowatt as the input energy, electrical energy to the system or electrical work on the system. We select control volume like this, and we have air, which its uh, volume flow rate is 150 meter cube per minute. So we have the electric heating system, which is being used in many houses, consists of simple duct with resistance heaters, like what you can see here. Air is heated as it flows over resistant wire. So this is air flowing to this resistant wire. Then its temperature is increased. And these the electrical work actually or power is 15 kilowatt. Air enters the heating section at 100 kilopascal and 70 degrees Celsius. So the uh, T1 and P1, which are the temperature and pressure of the air at the input of the duct, are 100 kilopascal and 70 degrees Celsius. So you can see the pressure actually is close to atmospheric pressure, and but the temperature is less than normal temperature of the room temperature. So we are interested to increase temperature of the air to increase temperature of the room, or we are going to heat the house or room. And the mass flow rate of this air which is flowing to this duct is 150 meter cube per minute. If heat is lost from the air in the duct to the surrounding at the rate of 200 watt, we need to determine the exit temperature of air, or T2. So we have a heat loss from this duct to surrounding as well, which is 200 watt. Then we need to find, so this duct is not insulated. We have heat loss from this duct to surrounding. Then we need to find this temperature, the temperature of the air at the output of the ducts. By common sense, we know that we have heater here, then temperature is going to increase. So T2 is going to be higher than T1. First of all, let's see what should be our assumption. We have a steady flow process like previous example. The time of control volume, the time of control volume are 0. Air is an ideal gas. Why? Because if we compare these properties for the air, temperature 17 degrees Celsius, pressure 100 kilopascal with the critical properties or critical temperature and pressure of the air, we understand that the air can be assumed as a ideal gas. And also we need to assume that kinetic and potential energy changes in this process for the working fluid or for the control volume are 0. And also assumption number 4 is constant specific heats at room temperature can be used for air, or CP of air reaction. We can assume that we have ideal gas, so we can assume that CP, or a specific volume, will be constant during this process for air. Then we need to select the control volume. We select the entire duct like what you can see here, the dashed line as our our system, and it is a control volume actually. We have open system. Why? Because the mass is crossing the boundary of our system, and it has only one input and one output. Our control volume is only one input, has only one input and one output. Then it means that 1, which is here, is equal to dot 2, which go out from the control volume. And we know that we have also heat loss from control volume, which is equal to 200 watts. Then, and also about that CP, which is the specific heat for air, we can find or we can assume for the air at the room temperature, or the temperature which we have here, is equal to 1.005 kilojoule per kilogram degree Celsius. This is the value of the specific heat at room temperature. But as we discussed earlier in previous slides or sessions, actually, this assumption is valid, and we can imagine that the CP for air with this temperature, 70 degrees Celsius, also is equal to the CP of the air with temperature of 21, which is room temperature. So CP is 1.005 kJ per kilogram degrees Celsius. Then we write energy balance equation for this control volume. As usual, these terms are zero. We have steady flow, then E in equal to E out, or E dot in equal to E dot out. What are E dot into the this control volume? W dot E in plus M dot H1, like what I have seen in the previous slides. And what are the output of our control volume? M dot H2 is the energy of the flow going out from the control volume, and also the heat transfer from the control volume to surrounding. Q dot out plus M dot H2. And as discussed earlier, delta KE, delta PE, changing the kinetic and potential energy for control volume are zero. And if we rearrange these, like what I have done in the previous slides, W dot E in minus Q dot out will be equal to M dot Cp times T2 minus T1. Then what the unknown in we are looking for T2. Then we have T1 from the question. We have T1, it is mentioned, and the we need to find. We have Cp, we have Q dot out, we have W dot E in. We don't know how much is the mass flow rate of the air through this duct or through our control volume actually. But according to our assumption, we know that the air is ideal gas. So we can use ideal gas relation like this, V1 equal to RT1 divided by P1 to find, first to find the volume flow rate, or to find the volume, a specific volume of air at the inlet of the duct actually. So R from the table for air as an ideal gas, we know it is 0.287 kilopascal meter cube per kilogram Kelvin. Time temperature, which we have here, is 17 degrees Celsius plus 273 convert to Kelvin to will be 290 Kelvin divided by the pressure at the entrance of the duct, which is 100 kilopascal. By calculation of this, we will have the specific volume of air at the inlet of the duct, which is 0.832 meter cube per kilogram. And we know that the mass flow rate of any flow or fluid is equal to the volume flow rate divided by the specific volume of that flow. This equation which we have used in previous examples as well, and that equal to that one, which is the volume flow rate, volume flow rate. V1 is a specific volume of the air at the entrance of the duct, and with that one divided by V1. With that one we have from the question instruction, it is 150 meter cube per minute, and V1 or sub V1, lower V1, we have calculated here. Then by substitution here and using this unity conversion, 1 minute is 60 seconds. We can find mass flow rate in terms of kilogram per second, which will be 3 kilogram per second. So we have calculated m dot as well. Then we substitute m dot in this equation as well. We have all of the information. Then T2. Then if we just substitute all of those information, we can find T2. We have W dot E in, we have Q dot out, we have M dot Cp and T1. Then only unknown in this equation is T2, which we can, by solving this equation, we can find T2, which is the temperature of the air at the exit of this duct. So by this we can find this equation. By this by this example, we reach end of this session, which was about the introduction or different some devices which contains a steady flow actually. In next session, we will start to discuss about unsteady flow, some devices which uh, with unsteady uh, flow flowing in those devices. Thank you very much for watching this lecture. See you next session.